السلام عليكم ورحمة الله وبركاته. Is my voice clear for everyone? And are you able to
Yes, Mustafa.
Are you able to see my screen?
Yes.
Okay. So without losing time, we are going to start. We are going to start today's session. In the last classes, or the last class to be precise, we have started the design of columns. Okay, in which we have taken some basics of designing of columns. We said we have different types or different classifications. We said in terms of columns we have bracing and braced and unbraced, and we have short and cylinder. We have talked shortly about them, and then we started saying that we have different types of columns, or different types of columns design according to the loading. We said that there are three cases. Case number one, whatever is called actually loaded, where we have only the value of n, and then we have second case, which is called actually loaded and uniaxial bending, in which we are having one loading and one moment. That moment can be about x or can be about y. And the third case, we said it is called actually loaded and biaxial bending, in which we are going to have one loading and we are having two bending moments. One is about x and the other one is about y. Furthermore, whatever we have taken, whatever we solved last class was about actually loaded. We have solved problem number one. I have told you to try problem number two. Hopefully, if there is time in this class, although I don't think so, okay, we are going to try problem number two. Now, since your final examination of this course is a little bit in the late end of the examination, I'm going to have revision classes. Okay, these revision classes are going to clarify your doubts. Okay, I'm going to solve more problems. You can bring the problems, I can solve them for you, and some of these problems might be coming for your final examination. Okay. Now, starting with problem number 3 directly, since problem number 1 and problem number 2 are for actually loaded, which you have tried in design of structures 1. I just tried to solve problem number 1 just to recap you, okay, for the design of actually loaded. But our main topic is going to be uniaxial bending and biaxial bending. Now let us go for problem number 3, and then later on we'll go for problem number 4. Now, if you see here in problem number 3, okay, in problem number 3, now the same things are available in your PowerPoint, but I brought them in the whiteboard, so later on I can give you the the session written already, so you don't need to write for this particular session. I'll be giving you the picture of whatever I have written for you in the class. Okay, now if you see problem number 3, it says that we need to design the longitudinal and shear reinforcement for a 275 mm square shore braced column, okay, which supports either, okay, case number A, ultimate axial load of 1280 and a moment of 62.5 kilonewton meter about the x-axis. Okay, and there is case number B, which we are going to deal with it later on. Now, if we see case number A, if we are going to see case number A, what do we have? We said general form is going to be n mx my. Now, for problem number 1, do we have a value of n? Do we have a value of n? For case number A, do we have a value of n? Okay, you will see that you have a value of n, which is 1280 kilonewton. Okay, what about moment of x? We have a moment of x, which is 62.5 kilonewton meter. and you will see we don't have a value of my. So in this particular case, which is case number A, we have a value of n and we have a value of mx. Okay, so it is not case number 1, which is actually loaded, where we are having only n value, but this is going to be actually loaded, which is n, and uniaxial bending means one bending only, which is either about x or y. In this problem, it is said about x-axis. Okay. Now, if you see this particular type of columns should be designed according to the charts. Okay. If you remember, in case number 1, which is only actually loaded, we have used this particular equation. We have used that n is equal to 0.4 FCU area of concrete plus 0.8 Fy into ASC. So this is used only for actually loaded, since this is not taking into account the moments which are available, okay, or the moments in the column, since the column is not having major moments. Now for uniaxial bending and biaxial bending, you shouldn't use the equation or this particular equation to design it. How we are going to design it? We are going to design it based on something called charts. Okay, we are going to design them based on something called charts. And if you see, this is the code which I have already uploaded for you since the starting of this particular course, which is BS8110 part number 3. Okay, you can see that the title of this particular BS code is the design charts for singly reinforced beams, doubly reinforced beams, and then rectangular columns. Okay, that also includes a square column, since it's going to be an even circular, since square is a special form of a rectangular column. Now, if we go and see, okay, you will see that the first chart is for singly reinforced beam. We are not designing beams now. Second is for singly. It keeps going for singly reinforced, and then we have doubly reinforced beams. We are not designing beams. We are designing columns. So we will come to the columns. So we have reached to the columns. This is the first sheet, or this is the first chart for the columns. Now you can see, whatever you can see, we have two axes. One axis which is n over bh, and the other axis which is m over bh square, where b has been given as the width of the column, h has been given as the depth of the column. So n is the loading, b is the width, h is the depth, m is the moment which is available in this particular column. Now there are different charts how to choose between this chart and, for example, the other chart. Now you can see the main differences between the charts when they are coming for the column. The first thing, you can see that here the FCU has been mentioned for you, that FCU is equal to 25. Fy is 460 always. Here we have d over h. What is the meaning of d? D is the distance from the top till the center of the reinforcement, which is whatever we called effective depth, and h is whatever we called overall depth. So the ratio between effective depth to the overall depth needs to be taken into account. Okay, so FCU 25, d over h is 0.75, and if you go and see the other chart, you will see that this is still for FCU 25, but now your d over h is 0.8. And then you can see the other chart is 0.85, and then the other chart is 0.9, and then the last one is 0.95. So for whatever grade of concrete, you will be having 5 charts, starting from 0.75, 0.8, 0.85, 0.9, and then 0.95. And we are going to see how to deal with these particular cases. Now, returning back to our problem, you will see that in our problem, the grade of concrete has been given to be 30. Okay, the grade of concrete has been given to be 30. So we're going to the code once again. Our 30 starts from chart number 26. Okay, So chart number 26 is having D over H of 0.75 and then 0.8 as we said, 0.85, 0.9 and then 0.95. Okay. Now we need to know which chart to be used in order to do that. Okay. In order to do that, we are going to calculate the value of D and H, get the ratios of D and H, D over H, to check which one or which of the charts is to be used. Okay, so we are going to go to the sheet once again, or the whiteboard here. Now, we know that already the cross section has been given, saying that this is 275 into 275 column. So my B in this scenario is 275 and my H is 275 as well. Now we need to get our D, which is your effective depth. And we have calculated our effective depth. We have calculated it. Okay, we have calculated, or we used to calculate it as D. Let us say that we have the bar here. We have a link as well here. Okay. So now we have D to be equal as D capital, or in this scenario H, which is the depth, minus cover minus diameter over 2. This is what we used to calculate. Okay, this is what we used to calculate. Now, one thing to be taken into account, that the cover has been given here, and this particular cover said to you that this is the cover to all reinforcement. Okay, so from the side of the element till the first part of the reinforcement, which is the link, this particular cover is 35 mm. Okay. Now, if you see in your BS code, if you see in your original BS code, if you are getting the values for the cover using the water and fire into account, or using the fire and water conditions, okay, you will see that they have mentioned for you, okay, they have mentioned for you that this is whatever we call it nominal reinforcement. Okay, or let us go and use the original code. Can you just mute yourself, please? Okay. So if you are getting the cover from these tables, okay, if you are getting the cover based on the water or fire conditions, you will see that you are going to use nominal cover. And this nominal cover says for you that it is already including links. Okay, so once again, if you are using the cover using these tables, already this value or whatever value you are getting from the table is already including the diameter of links. Now, in this particular problem, okay, you didn't get it from the table. It says for you only cover to or reinforcement to, so it means till the first reinforcement, which is the link. So now, if you are using nominal cover, then this is your equation. If you are using clear cover, in clear cover, your diameter of link is not included. So link plus diameter over 2, which is for the mainstay. Once again, in nominal cover, if you are using the table, it's already including the diameter of the link. so you don't need to take it into account. If you are using a clear cover, then you need to take the links into account. So now if you say my D is equal to, we have 275 minus the clear cover which has been given to be 35 minus diameter of the link. Normally we have diameter of the link. Now of course this is going to be minus, not plus. Okay, so minus the link diameter is regularly 8. We can go and use, for example, a diameter of 20. Okay, we are going to use a diameter of 20. So 20 divided by 2. Now, can you give me the value of D? Can you give me the value of D? Okay, so we have got our D. We have got our D to be 222 mm. Okay, can we get now D over H ratio? D over H ratio is 222 divided by 275. Can we get this ratio? It is 0.807. Okay, it is 0.807. Now you see, whatever we said we are having 0.75, and then we're having 0.8, and then we're having 0.85 for the ratios, I mean for the charts, and then we're having 0.9, and then we're having 0.95. Okay, anything lesser than 0.75 or equal to 0.75, you will be taking 0.75. Anything more than 0.75 till 0.8, you are going to take the chart of 0.8. Anything which is more than 0.8 till 0.85, you will take 0.85. And then anything from 0.85 till 0.9, you will take this one. Anything from 0.9 to 0.95, you will take 0.95. Now, of course, you will not be having something more than 0.95. Okay, because if you are reaching to 0.95, it means that you are providing less cover. Okay, you are providing less cover, which is not a valid design of a column. Okay, now which ratio should we take, or which chart we should take? Is it the 0.75, or is it the 0.8, or 0.85, 0.9, or 0.95? Okay, so we use 0.85 chart. So we are going to go to the charts once again. So we have this chart for 0.75, we don't require it. 0.8, and then we went for the 0.85. Okay, so we have 0.85 chart. Just bring it here. Okay. Now, if you see, once again, if this is my chart, okay, if this is my chart, my FCU is 30, my D over H is 0.85. Now you will see that I have two excesses. One is M over BH square. The other one is N over BH. Okay, N over BH. Now, if I wanted to calculate N over BH, you can see that my N, okay, you can see that my N from the beginning has been given as 1280. Okay, so 1280 into 10 to the power of 3. Okay, since it's in kilonewton, because you can see that these ratios should be in Newton. B, what is my B? My B is 275. What about the other B, or the other dimension? Once again, the depth is 275. Can you give me this ratio? Can you give me this ratio? Sixteen. Okay, no problem. 16.9. Okay, let us say 16.9. So we have got the value of n over bh. We need to get the value of m over bh square. So we have m. What is the value of m? Once again, we'll return back to the question. Okay, we'll return back to the question. You will see that the m value is 62.5. Okay, so we are returning here. It is 62.5. We are multiplying it by 10 to the power of 6. Since it was kilonewton meter, we are converting it to Newton millimeter. So 10 to the power of 3 and then 10 to the power of 3. B is 275. H is 275 and it says square. How much is this value? How much is this value? Okay, so it is going to be 3. Once again, it is to the power of 6, not the power of 3. Okay, it is to the power of 6, not the power of 3, so be careful. It is a moment, so it needs to be 10 to the power of 6. Just to make it easy for you, any force, it should be multiplied to the power of 3, any moment to the power of 6. So now we have two values. One is 16.9 and another one is 3. Okay, so what we need to do, now this is the point. Let me just try to zoom. Okay, so this is the line of 3 for m over bh. This is the line approximately of 17. Okay, now if we try, now just roughly, you don't need even to use a ruler, but roughly you can take it as it is touching here. Okay, so this is my point. Okay, so this is the point roughly. Now you can see, okay, you can see that there are different curves here. There is this curve. Okay, there is this curve. Can you see? And there is another curve, and it goes on. Okay, now these curves are representing the percentage of reinforcement. The minimum percentage of a column or minimum percentage of reinforcement in a column is 0.4%. From where we have got that? We have got it from, okay, we have got it from the code. Okay, we have got it from the code. So once again, we'll go to the code, to the extract. We'll go for minimum and maximum area of reinforcement. Column is a compression member. Okay, column is a compression member. And it says for you a rectangular column or a wall, it has a minimum reinforcement or minimum percentage of reinforcement to be 0.4%. So the minimum is 0.4%. What does it mean? It means that if you got any point in this particular region, it means it is lesser than the minimum. lesser than 0.4, and you will be taking 0.4. Okay, any value here, it is going to be something more than the maximum. And if it's more than the maximum, of course, you cannot use the maximum because your load will fail if you are reducing it. What you need to do, you need to increase your cross section. If your loading is more than the maximum percentage of reinforcement or causes you to have more than the maximum, then you need to increase your cross section of the element. Now you can see my point, which I have drawn, it is touching which line? It is touching which line? You can see we have the line of 0.4 and then 1 and then 2 and then 3. You can see that my point is touching the line of 3. If it's between 2 and 3, I will see whether it's close to 2 or it is close to 3. Like for example, if it's here, then I can say, for example, it is 5.2. If it's closer to the 6, then I can say roughly it is 5.8. This is a rough way of finding your area of reinforcement. Now what I have found that my percentage of reinforcement corresponds to it's touching the curve of 3. So my 100 AS over BH, according to whatever has been given here, is equal to 3. So my AS is actually 3 divided by 100, or 3% of B into H. Where 3 divided by 100 multiplied by 275 into 275 will give you your area of reinforcement. Can you give me your area of reinforcement now? Can you give me your area of reinforcement? Okay, it is 2,269 millimeters square. We said area should be a whole number. Okay, so 2,269 approximately. Okay, can you just confirm this for me? Okay, so it is 2,269 millimeters square. So this is my required, okay, this is my required area of reinforcement. Now what I'm going to do, I'm going to go to the code. Okay, I'm going to use this table. Now what is my diameter? My diameter is 20 mm. I need to check value which is more than 2,200. So if we see, if I choose 1 bar, now of course I cannot use 1 bar because the minimum number of bars is 4. Okay, why they have supplied you 1, 2 and 3 if the minimum is 4? Because you can combine different diameters. Okay, I can have 3 bars of 20 plus 1 bar of 16, for example. Okay, that can be done as well. Now for us, we are having 1 diameter only, which is 20. So we will go, you will see that the closest one is going to be 8. Okay, the closest one is going to be 8. And once again, when you are doing a designing of a column, always make sure that you are having an even number, not an odd number as a reinforcement, out as a number of reinforcement. Okay, you cannot choose, for example, 5, because you cannot place 5, you cannot place 3 in a side and 2 in a side. Okay, so either 3 and 3 or 2 and 2, depends on how much is required. Now once again, you can see, according to 20 mm diameter, 2,200 is not sufficient, so I'll go and take 2,510, which corresponds to 8 bars of 20 mm. Okay, so I'll go to my whiteboard and I'll say, okay, adopt, let us say 8T of 20 diameter. Okay, 80 of 20 diameter. 8 is the number of bars, 20 is the diameter. Okay. Now we know we knew our main reinforcement. We are going to go for something else, which is your links. Okay. Now for the links, what we need to do? Okay, for the links, what we need to do? We will go once again to the BS code and read what the BS code says for the link. Okay, so we are going to go for the chapter of columns. For the chapter of columns, and we are going to search for any clause saying anything about my links. Now these are the things which I have told you last class about shortened cylinder, braced and unbraced. These are explained as well in your code. Okay, so it says here, it says for you here, when part or all of the main reinforcement is required to resist compression, which is the column. The column is the compression member. Can you mute yourself? Okay. Links. Okay. It says for you, if you are designing for a compression member, you need to provide at least 1/4 the size of the largest compression bar, or 8 mm, whichever is the greater, and it should be provided at the maximum spacing of 12 times the size of the smallest bar. Okay. So we'll return back here. There are two things when we are taking the links into account. One is the diameter. Another thing is your length. I mean, is your spacing. Now for the diameter, if you return back to the code, it says for you at least 1/4 of the size of the largest compression bar, or 8 mm. So we have two cases. Case number 1 corresponds to 1/4 into largest compression bar. Now we have only one diameter, which is 20. We don't have a combination of different diameters. Okay. So if you have, like, for example, different diameters, you should take the largest one. So 1/4 multiplied by 20, this is going to give you 5 mm. And then the second case is 8 mm as per the code. Once again, the code says for you 1/4 the size of the largest compression bar, or 8 mm, whichever is the greater. Okay, whichever is the greater. Now, of course, why would I choose the greater? Because it's better for me to have a bigger size of diameter. It is safer. Okay, so 8 mm is going to be my diameter of the link. Now, what about the spacing? Once again, according to my code, the spacing says 12 times the smallest compression bar. Now, why here it says smallest and in the diameter says largest? Now, of course, for the diameter, it's better for me to have a bigger diameter. For the spacing, it's better to have a smaller spacing. Smaller spacing means more reinforcement. So 12 times of the smallest compression bar. Once again, in this problem, we don't have, or regularly when it comes to column design, we don't have a combination of different diameters normally. Okay, so 12 times of whatever diameter you are having. So 12 multiplied by my diameter. My diameter is 20, so 12 into 20 is going to be 240 mm. Now, just to conclude, we are going to draw our detailing. So we have, this is my cross section. Okay. We have our links here. Okay, we need to supply 8 bars. So this is 1, 2, 3, 4, 5, 6, 7, and then 8. Okay, 8 number of bars. Now, of course, the four reinforcement bars which are available in the corner are held in position because of the links, but there is nothing protecting the inner bars. So you need to supply another link here, and you need to supply another link here, or to be accurate, not like this. Okay, and then here. This is my cross section where these are my 8 T20 diameter, 8 bars of 20. The blue and green colors are representing, we say, 4 legs. 4 legs. So this is 1, 2, 3, and 4. 4 legs for the links. Okay. What is your diameter? So I will say T 8 diameter at 240 mm center to center. Okay. So this is the design of a column. This is normally a 10 marks question in the final examination. Okay. Doing that, we have done the design of a uniaxial bending. If you want as well, you can draw the 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 elevation or the section in which you are going to show the bars. So we are having bar number 1, bar number 2, bar number 3, and then bar number 4. I can see 4 bars, and then there are links linking these bars together. Okay. Now this is regarding uniaxial bending, actually loaded and uniaxial bending. Now, whatever we have learned from this, we have learned that we need to use, the charts in order for us to get our area of reinforcement. Now, what about the second scenario? Okay. What about our next second scenario, which is scenario number B? Let us go here. Now, scenario number B. Okay. Scenario number B, you will see that we are having N, MX, and MY. N value has been given to be 1280 kilonewton. MX has been given to be 35. And then MY has been given to be 25. Okay. In which, when I'm going to draw my section, so this is my x-axis, this is my y-axis. The moment around this axis is called mx, and the moments around the other axis is called my. If this line shifted somewhere here, then it is called my. If my point comes here, then we call it my. Why? Because your y-axis has shifted to somewhere else. If my point came here, then I can say that this is going to be because of mx. Okay, we have mx value. Why? Because my x-axis has shifted to somewhere else. Now, if we have a point here, for example, then this is a combination of both x-axis and y-axis. Okay. Now, coming back to the question, we have been given the value of n, we have been given the value of mx, and we have been given the value of my. Now, in order for us to design, we need to know what is the procedure. Okay, what is the procedure? We will go to our code once again to verify the procedure. Okay, so if we are going to the code, this is what I explained for you now. Okay, now you will see that this mx, according to my diagram, this mx is resisted by this dimension. It moves in the direction of h. Okay, so mx is resisted by h. My is moving in this direction, so it is resisted by b. Okay, according to this geometry. Now it says for you for biaxially loaded. Okay, for biaxially loaded, we have mx over h dash if it's more than my over b dash, because mx was related to h, my is related to b. Okay, if your mx is more than my, okay, you will be having the resultant to be mx. If your mx is lesser than my, you are going to have the resultant about y. It is like we are having two particular forces and we are trying to get the resultant. Okay. So what we are going to do, we are going to take these particular ratios first, mx over h and my over b. We will see whether we are going for case number A or case number B. What is the meaning of h dash and b dash? They have been mentioned here. So h dash is the effective depth in h direction. B dash is the effective depth in b direction. Returning back here. Okay, so we need to get the value of mx. Let me change the color. Okay, so we need to get the value of mx divided by h dash. So my mx is going to be how much? My mx is 35. Okay, 35. H dash, the distance, if this is my h dash is the distance from the top till the center of reinforcement, which is available here, which we have already got it as the value of d small, if you remember. H dash is something similar to d small, which we have got in the previous calculation as 222, because my cross section didn't change. Okay, so 35 divided by 222. The other side, we're going to have my divided by b dash, where my is 25, and then my b dash. Now, once again, the other dimension is b. We need to calculate the distance from this point till here. This is my b dash. Now, if you see in your column, it is 275 into 275. So your b dash is equal to your h dash, which is 222. If it's not equal, then you need to calculate them separately. Now, can you get me these ratios? Or eventually, can you tell me which one is bigger? Which one is bigger? mx or my? Now, directly you can know that mx is going to be bigger since 35 is more than 25. And they are divided by the same value. Okay, mx is going to be, of course, more than my since 35 is more than 25. Okay, so now what we are going to say, since the dominant moment is x, we are going to calculate mx dash. Okay, my mx is more than my. Okay, so this is 0.15 0.578, and this is 0.1126. Thank you, Ashwa. Okay, now you can see that mx over h dash is more than my over b dash. According to the code, according to our code, it says for us, if your mx over h dash is more than my over b dash, the dominant is going to be x, so we are going to calculate mx dash. How to calculate this mx dash? It is calculated as mx plus beta h dash over b dash multiplied by my. We are taking the full of mx plus a ratio of my. If my is the dominant, we are taking my plus a ratio of mx. So we are going to write this particular equation now. Okay, so my mx, okay, my mx dash is going to equal to mx plus beta, okay, h dash b dash into my. Now my mx is how much? My mx is 35. Beta, how to calculate the beta? If we go to the code once again, my beta is equal to 1 over or 1 minus 7 divided by 6 multiplied by n divided by bh into fcu. Okay, so I'm just going to calculate it here. Okay, my beta is equal to 1 minus 7 over 6 n bh fcu, where 1 minus 7 over 6 n, how much is my n value? 1280 into 10 to the power of 3, 275 into 275 into the grade of concrete, which is 30. Can you get me this value? Once again, this is the equation. 1 minus 7 over 6 multiplied by n divided by BHFC. Or you can get it from this particular table. Okay, but rather than using the table and the intersection, it is better to use this particular equation, which will give you the coefficient directly. Okay, so we have got it around 0.34. We have got it around 0.342. So I'm going to write it as 0.342. Okay, 0.342. H dash is how much? 222. B dash 222. So these are going to cancel with each other. Multiplied by my. What is your my? My is my 25. Now can you get me this value? Can you get me this value? My mx dash is going to be 43.55 kilonewton. Okay, so what we have done, we have tried to go and have the resultant of two moments into one single moment. Okay, which is going to be used for m over bh, and already m over bh square, and already you have n over bh. You have the value of n, you have the value of b and h. You have the value of m now, which is the newer one, and then you have b h b into h square. Okay, so once again, in case of a uniaxial, you are ready, because for the charts, to use the charts, you are required to have one m and one n. So you have in uniaxial, you have already one n and one m. In biaxial, there are two moments in where I need to get the resultant. How to get the resultant? The code has given you. There are two cases, either case A, if mx is dominant, or case number B, if my is dominant. Okay, in which you will have only one final moment. Okay, that final moment is going to be used as your resultant moment, as your single moment, and you have one n, and then directly you can use the chart as whatever we have done in the previous problem. Okay, and accordingly you will be able to calculate the area of reinforcement, and you will be able to calculate the length. Any question till now? Any questions till now? Okay. Now, question number or problem number 3 or problem number 4, sorry, we have just solved problem number 3. Problem number 4, I'm going to solve it in the revision classes. Okay, problem number 4, I'm going to solve it in the revision classes. Now I want to go for some other points as well. Okay, just concentrate here with me. This is a good reference which is going to be used for when you graduate, when you work on your project, or even when you prepare for your final examination. Now you can see that we have let's say a single story building. Okay, a single story building. We have 1.5 meter from the foundation level to the ground. Okay, normally the range is from 1.5 to 1.8, and then we have one story which is 3.5, and we want to design. Okay, we want to design the columns. I have told you that your dead load is equal to 2 kilonewton per meter square on the slab, and then life load is equal to 2 kilonewton per meter square. Okay, and for example, I said that I'm going to design this particular column. Now what we should do, now if you see whatever problems we have solved or whatever problems that you have got earlier, you have got the loading ready. Now that's not the case in when you are going to work it out yourself. When you are going to work, or whenever you are going to work on your project, you need to calculate your value of, the value of loading. Now if you see, so this is a 3D, and then on the right side we have our plan. So we have like the depth of the slab to be 150 mm, and they have given us that the column size is 200 into 400, beam size is 200 into 400, and we know that the spans of the slabs are 5 meter, 5 meter, and then 4 meter. Okay, it can be seen here, 5 meter, 5 meter, the length for each one, and the width is 4 meter. Now, if I want to go and draw it, just concentrate here with me. So this is my arrangement. Okay, we have a column here, column here, column here, a column here, a column here, and then a column here. The distance is 5 meter here, 5 meter here, and this is going to be 4 meter. Now you have two methodologies. Okay, you have two methodologies. Either you can cut it as whatever we have said, if you remember. And you will see that this particular column is actually going to take half of the trapezoidal, half of this trapezoidal, half of this trapezoidal, half of this triangle, and half of this triangle. And you can see now this particular length from here to here, this is going to go as 2.5 from the left side. This is 2.5. This is 2.5. So this goes as 5 meters. Okay. This goes as 2 meters. Okay. So now what I can say that this column is actually taking okay, is actually taking an area of 5 into 2. Okay, so what I need to do, I need to go and calculate W of slab. For W of slab, we have three loads. One is the self weight, which can be calculated as 24 into the depth of the slab, which is 1.15. And then we need to multiply it by 1.4, since it's a dead load. Plus, we have another loading, which is the dead load. So that is 2, and then we need to multiply it by 1.4, which is a factor of safety. Plus, we have 2 as a life load, and we need to multiply it by 1.6. Now, can you get me this value? Can you get me this value? Not possible. Okay, so this is going to go as 11.04 kilonewton per meter square. Now, the loading of the column, if you remember, the loading of the column is available in kilonewton. Okay, the loading of the column is available in kilonewton, so we need to multiply by an area. Okay, we need to multiply by an area which is 5 into 2. That is the area which is carried by, okay, which is carried by the column, okay, which is carried by that particular column. Now, can you get me this value? Can you get me this value? 110.4 kilonewton. Okay, so this is the first loading. Okay, let's say loading number 1, which is coming from the slab. Okay, the second loading coming on this particular column is the self weight of the beam. Now, whatever we have calculated till now is the weight of the slab. Okay, and then we have, if you see, if this is my column, you will see that this column is attached to a beam here. Let me just write it. Self weight of beams. Okay, we have one beam here and we have another beam here. Now you can see this beam is actually 5 meter. Half of this 5 meters should go here, half of it should go the other side. So it means that this dimension is 2.5, this dimension is 2.5, and the other dimension here is 2. Okay, so we have this one. We just draw it in another color. So this is 2, this is 2.5, this is 2.5. Okay, so this is 2, 2.5, and then 2.5. Now, self weight, which is coming on the column from the beams, is going to be, what is the self weight of the beam? 24 multiplied by the size of the beam, which is 0.2. We said from the cross section, we say 200 into 400. Okay, so it's 0.2 multiplied by 0.4. Okay, now we don't want it in kilonewton per meter, we want it as a kilonewton, so we need to multiply it by the length of the beam. Okay, so multiplied by 2.5. Once again, the loading on the column is going to go as kilonewton, not as kilonewton per meter. So 24 multiplied by 0.2 multiplied by 0.4 multiplied by 2.5. This is for the first beam, which is beam number 1 here. Then we have beam 2, and then we have beam 3. Okay, multiplied by 1.4. because it's a dead load, plus the second beam is 24 into 0.2 into 0.4 into the length of the second beam is 2.5 once again, and it's multiplied by 1.4. The third beam is 24, which is density of concrete, multiplied by 0.2, multiplied by 0.4, multiplied by the length of the beam, which is 2 meters, once again multiplied by 1.4. Now this can be summarized as 24 multiplied by 0.2 multiplied by 0.4. 2.5 plus 2.5 plus 2 is going to go as 7 multiplied by 1.4. Can you get me this value? Okay, so this is 18.816 kilonewton. Now you can see that we have taken the slab's load, we have taken the beam's load or the beam self weight. The remaining thing is to be taken, or the last thing to be taken, is the self weight of the column itself. Now, how to calculate the self weight of the column? Self weight of column is equal to 24 multiplied by B multiplied by D multiplied by the length of the column. Okay, and since it's a dead load, it's going to be multiplied by 1.4. So we have 24 multiplied by B, that's 0.2, 0.4 into L, the length of the column. Since we are solving for this column, for this particular column, then the length, you can see it is 3.5 meters. So 3.5 multiplied by 1.4. Can you get me this value? Can you get me this loading? 9.408 kilonewton. Now you can see total loading on this column is going to equal to load 1 plus load 2 plus load 3. So we have 9.408 plus 18.816 plus 110.4. Can you tell me how much is your total loading, which is N value? It is going to be around 138.624 kilonewton. So this particular column should be taking a load of 138.624. Now, if I want to include or I want to design now this particular column, if I want to design this particular column, now you will see this particular column is going to take beam number 1, beam number 2, beam number 3. There is no slab because it's a ground floor, plus it is going to take the n value of this column, let's say upper column. Okay, now you will see the beams are the same. The beams are the same for the bottom column, but the only difference, rather than taking it 3.5, we are taking it as 1.5 now. Okay. Now, if we are going for the bottom column, if we are going to go for bottom column, then self weight of beams is going to equal directly the same as whatever we have done it for the upper column, which is 18.816. There is no loading from the slabs because there are no slabs to be designed in the ground floor. We said for the ground floor, the loading is taken directly by the soil. The only thing which will change for you is the self weight of the column. Why? Because when we have calculated, we have taken the height to be 3.5 meter. Now the height of this particular, or the length of this particular column is 1.5 only. So it is going to be 24 into 0.2 into 0.4 into 1.5 multiplied by 1.4. Okay, now can you get me? And then plus it is taking n from the upper column, which is 138.624. Can you give me the total of this particular loading? And for lower column. Can you give me the total? No, that cannot be done. 24 into 0.2 into 0.4, 0.5, 161. Okay, so 161.472 kilonewtons. Okay, so this is going to be, okay, this is going to be my loading, or this is how to calculate the loading when it comes to real structures. Okay, now if you see, here, now for this particular foundation, assuming for example that we have, let's say 2 into 2 meter, okay, 2 into 2 meter. Now we learned that the loading coming on this column is whatever we have calculated for the upper. It should be designed for that, and this is whatever we calculated for the lower. Okay, what about the foundation now? We learned that when we design the foundation, we are going to take into account the loads from the column, we are going to take into account the self weight of the foundation, and we are going to take into account the backfill. So if we want to design this particular foundation, what are the loads to be taken into account? So first, we are going to say that the loading, which is P on the column, is going to be N from lower column which has been calculated as 161.472, plus we are going to take into account the self weight of the foundation. Self weight, if this is in kilonewton, of course your self weight should be in kilonewton. And how to get the kilonewton? It's going to be 24 multiplied by 2 meter into 2 meter multiplied by, let's say, the depth of the foundation is 0.5. We are assuming for the foundation is 0.5 meter. Okay. Now there will be a backfill. Okay, there will be a backfill. So this is self weight of footing, and then there will be a backfill. Okay. Now for the backfill, to understand the backfill, this is my foundation in terms of a section. This is in terms of a plan. We have a column which is, let's say, 200 into 400. Okay. Now the foundation is located at the depth of 1.5 meter. From this 0.5 is going for the foundation. So the backfill will only be available. This is my ground level. Natural ground level. Okay, which is going to be 1 meter. So this particular depth is going to be for the backfill. Now if you see, the backfill will not be in the position of the column. The backfill will be only in the other position. So if I want to calculate the backfill, I need to calculate the area of backfill first. That is going to be 2 into 2, which is the area of the foundation minus the area of the column. This is my area. What is the depth of the backfill? The depth of the backfill is going to be 1 meter. Okay. Now how much is this? How much is this? Three point 3.92 meters square. This is area of backfill. Now, in order to transfer it to a load, I need to multiply it by density, which is density of the soil, since the backfill material is soil. And normally, the backfill density of soil is 18 kilonewton per meter cube. Can you just multiply this? Sorry, this is in meter cube. This is area. This is volume now, not area. Okay, so area multiplied by depth. This is my area, which is 2 into 2 minus 0.2 into 0.4. Depth is 1 meter. Okay, so 70.56. This is a backfill load. So my foundation should take the loading coming from the top, which is 161, plus it should take the self weight of the footing, plus it should take the backfill. Okay. Coming back to our topic, we have calculated for the columns the value of n. We need now to know the values of moment, because we said the columns are designed for moments and loading. Now, if you see, for example, let us say that this is my, let me just draw it as an X. This is my first X, this is my second X, this is my third X. The distance here is 5 meters, and then we have 5 meters, and then we have here, for example, 4 meter. This is whatever we had it in our plan. Okay. Now, if you see, this can be idealized as this, in which you're having your loading on the beam. This is having a length of 5 meter. This is having a length of 5 meter. What is your W? This will be the W of the slab, whatever loading is coming from the slab plus self weight of beam. Okay. Now the actual shape is actually a UDL plus either a trapezoidal or triangle. But for the simplification, what we are trying to do, for the simplification, we are going to take it as a UDL. Okay. For manual calculation, we are always simplifying it into a UDL. Now, what is the loading of the slab? If we return back, okay, the loading from the slabs, if we are taking the top column, the loading from the slabs is 110.4, but we don't want it in this form. We want it as a UDL. Okay. So we have 11.04, which is kilonewton per meter square. Now, this height of the trapezoidal is 2 meter. From where we have got it to be 2 meter. From where we have got it to be 2 meter. We have got it from here. Okay. This is 4 meter. So if we try to have the trapezoidal, if you remember, we said this is going to be Lx over 2. So this is 4 over 2. That's going to be 2 meter. Okay, so we return back here. Okay. So that was how much? 10 point how much? 11.04, sorry. Okay. So loading is going to be 11.04 multiplied by 2. This is for the weight of the slab plus the self weight of the beam. The self weight of the beam is how much? It is 24 multiplied by 0.2 multiplied by 0.4. Now we are calculating it as a UDL, so we don't need to multiply by the length. Multiplied by 1.4. Can you get me this value? Can you get me this value, please? This is 11.04. $24.768. Okay. So now, if I have a fixed end moment, a fixed end beam, where my W is 24.768, so 5 meters, you will be having a bending moment goes like this, where this moment is equal to W square over 12. and this moment is W square over 24. Now we don't require the 24 one because we are designing for the column now. So this is 24.768 multiplied by my length, which is 5 square, divided by 12. How much is this? How much is this? Okay. Just cross-check and verify the values of whatever you are giving me. Okay. So now 51.6. So we're going to have 51.6 here, 51.6 here, 51.6 here, 51.6 here. Since the lengths are the same, the loading is the same, this will be cancelled with this. You will see that this, okay, this is in one side. Now what about the other side? So that's the side of X. What about the side of the other side? Now you will see, we said there is a moment here, there is a moment here. Okay. Now here we don't have any moment because they cancel each other. They cancel each other. Now what about the other direction? What about the other direction? The same thing, but now rather than having 5 meter, the length of the beam in this scenario is 4 meter. And once again, it's UDL taking a slab load and taking a self weight. So this is going to be M is equal to WL square over 12, 24.768 multiplied by 4 square divided by 12. Can you give me, now rather than 4, it is, rather than 5, it's 4. Can you give me this value? Thirty-three point 024 kilonewton meter. Now you will see we have 33 in this side, okay, and we have 51.6 on this side. Here we have 33.024. Here we have 33.024, and then here we have 51.6. Now you will see this particular column is designed as uniaxial because only we have one value of moment and there is a value of n, of course. These two locations, this one, okay, these two locations are designed as a biaxial, okay, because we have two moments. Now the question says, shall I put my column in this particular zone? I have a moment in this direction of 51.6. I have a moment in the other direction to be 33.024. Shall I put my column in this side as this is my 400 into 200? Or shall I keep my column like this, where this is 200 and this is 400? Okay, the good engineer is always going to keep the biggest moment with the biggest dimension. Okay, the biggest moment with the biggest dimension. Now you can see that 51.6 is more than 33.024. So 500 or 400 as a depth should go with the same direction of 51.6. So if I was the one to do the column positioning here, this should be going in this direction. This should go in this direction. This can go in the other direction. Okay. Doing this, we have finished today's session. We have finished almost the course. Uh, there will be a couple of revision classes, as I told you. In these revision classes, I'm going to solve whatever questions that you are having. Hopefully, your final exams is going to be easier than whatever you had, so you can get better marks. And we have finished this particular session. Thank you very much for being patient with me, and hopefully we'll be meeting you soon in the industry, and we are going to see you as big future engineers, inshallah. If you have any question, you are free to ask. If you don't have any question, then we finished today's session. And at the end, once again, I'm honored and privileged to have students like you. And always try to keep learning. The process of learning should not be finished, whether you graduated or not. And hopefully you will make Oman a better place, inshallah. You will do a better job than us, inshallah. Any questions?